First thing to do, factor everything. Before you reduce, go for your domain restriction, because everything in that denominator you cannot use. So take your domain restriction out first. You cannot use a -2 or a +3. The factor that you take out, and as soon as you cross it out, right next to it, the point of discontinuity. Because if you don't, you're going to forget to go back to it, because that's the point that you can't use. And on your graph, it doesn't look like it's not there. When you graph it, it goes right over this. This looks like a very nice little graph with a couple of asymptotes in it. But your calculator cannot stop at this little tiny speck and go over it. But you can notice this in your table. In your table, it will say error. So make yourself a little note to come back to that. Write this out. Make sure you write this into reduced form. That's what you're going to use for the rest of this. Okay? Your vertical asymptote is what's left in your denominator. This guy is left. There's your vertical your asymptote. Your horizontal asymptote, go by your rules. The degree in the numerator is the same as the degree in the denominator. Make a ratio, 1/1. So there's no slant if there's a horizontal. Point of discontinuity, make sure you bring that down. Make sure you substitute it back into the one that's reduced, not into the original one, because it won't work in the original one. So find your point, because it's an XY point. Find your point, and just kind of put a little open circle in your graph somewhere.
Oh, for the point of discontinuity or whatever, why'd you make it 3 plus 9? Right, like
well, we took whatever was reduced, our function after it was reduced, and we have to find the y value associated with that. We found the x value to be 3, so the y value, therefore, would be 3, plug it in for x.
So
wait, that would be
3 plus 6? It would be 3 plus 6, not 3 plus 9.
3 plus 6. You know, I probably said 3 plus 6 and added it to 9 and wrote 9.
Yeah, that's fine.
You got to keep me honest. Okay, so keep it, if you want to make this a decimal, that's fine. And it's a terminating decimal. It doesn't matter to me what you call that, as long as you give me a point. Remember, if you put this in your y1, you put this in your y2, the reduced one, it will look like the same graph, but what happens is you eliminated your point of discontinuity. So you won't be able to see that. You will have a regular 3 in there. What you can do is look for that and see what your 3 is, because you eliminated it. Or we can use the calculus approach. We can look at 2.99999. We can look at 3.00001 and see that both approach 9/5. So you can look at it that way. That's how we do it for limits with calculus. And we'll be tying that together. Unfortunately, we tie it together at the end, so we revisit these. So I like you to be aware that this is what's coming down the pipe. This is where it's approaching on both ends. So it has a limit to it. It has a little point that we can actually fill in. Make sure you do these algebraically. Still, zeros of your numerator. If you put y equals to 0, as soon as you cross multiply, your zeros of your numerator. Zeros of your numerator. Your y-intercept is the easier one. Concave down. Be careful, take out your point of discontinuity in these guys. They look like they make a nice concave up, but he's missing a little point right there. So make sure you take out that point of discontinuity. Your range, do your range last if you like. Increase, decreasing. Increasing, there is none. Decreasing, watch your point of discontinuity. How does that work for you guys? Good? Any questions? Questions, hang-ups? Yes.
For the horizontal asymptote, you did like the 1/1. That was from the x squared over x.
Your second rule is when the exponents or the highest exponents are the same, you take a ratio of their coefficients. We generally say a over b. We just say a over b. Top over numerator over denominator. Use that sheet. If you use that sheet, it's kind of helpful because there's so many things to find. And I kind of said make sure you remember to factor, reduce. If you try to plug this 3 back into this original one, 3 it's going to give you a 0 in your denominator, and you're going to say undefined. And we know that point is undefined. But if we could fill that point in, if we could eliminate that point and reach a limit to that point, it would be this y value. And again, confirm it on your graph. Your graph is really helpful for this. Okay. I think there was one tricky one where it crossed over. I honestly don't know what happened to this writing. It got a little weird. I don't know what happened to it. But you should be able to still read it back there. Every once in a while it does something strange on me. But this one kind of works exactly like the other one works. Factor everything. Before you reduce anything, find your domain restriction. Take out everything from your denominator. Once you factor, give it to me a reduced format. This is what you're going to use after this. And again, find your point of discontinuity. Label it somewhere. Because, you know, sometimes you don't go back to it because you don't see it on the graph. So make sure you go back to your point of discontinuity. Plug that x value into that reduced function. Concavities, range. Nope. No intercepts. So find your x-intercept and your y-intercept. X-intercept is zeros of your numerator. And your y-intercept would be negative 4 over 2. I must have erased it and redid it, and something weird happened to it, so I don't know what happened to it. I might have changed it. Everybody okay with this one? Yes. Concaves. Concaves are harder when they look like this because it's still going into a down motion. Normally, when we concave, they kind of look like they kind of come back up again, or they kind of go back down again. But on these, because there's no max or min here, they're still making a concave up. This is still making this go up, like figure out that it goes up here, and figure out it goes down here. So your concavity says, just like your increasing, decreasing, always go by your x's. So my concavity says, I would go from 1 to infinity. That would be my concave up here. However, I got to jump over this point of discontinuity. Because technically when I make this, I have to stop here, jump over it, and then continue. So it is not a continuous part of my function. So same thing with your increasing, decreasing. Your decreasing and your concave up will look exactly the same as this part. So come from negative 1, jump over this part here. What is this point of discontinuity? 2. 2. Jump over the 2, and then from 2 to infinity. And your concave down, this is kind of like a concave down motion, figure it. And you're concaving down here. Your cave, if you did it, like would look like this. So kind of picture it just concaving down. Picture that one just going up. That was one of the things that always threw me off too. I was never fond of calling that a concavity because it technically keeps on going out. It really doesn't come in, but they call it a concavity. That was one of my things I always questioned. Any other questions on this? Well, you can't, because what happens is, in your calculator, it's not there. Let's put this in. It's missing, so you can go like, what's our point of discontinuity? 2 something, so the x is 2. You can go to 1.99999, you could go to 2.00001, but if you go to 2, it's blank, because there is no point there. So in calculus, we call this reaching a limit. If your function from both ends converges towards the same point, then we call it, that's the limit that we reach for that function. So if we say, and we write it like this, the limit as x approaches 2. Because sometimes there is a point, sometimes there's not a point there. So as we approach 2, what would that y value be? If we could actually fill that in, this is called the removable point, because I can actually fill it in. I converge from the left and the right to the same point. If you look in your table, it says error, because there is no point. There technically is none. But if you go 1.999999, 2.00001, it'll converge at that point. I can't find it. It's probably underneath there. Whatever that y value is, that's the value that you'll see. Okay. Do you want me to put this in and look? You sure? Okay. It takes me longer to work that calculator. So here it is, 2, 4. You won't see the 4 in your table. It'll say this. Because technically there's no point here. But if you do an x value of 1.99999 and an x value of 2.00001, your y value will be very, very close to 4. So the limit, and this is how we write it in calculus, as x approaches 2 would be equal to 4. If I could fill that in, this is a definitely removable point because I could be able to put my pen down, go right through it, and close it. Okay, this one was the tougher one, this last one. Oh, you didn't have a point of discontinuity here? Oh, that was 6, okay. This one, oh, this one wasn't bad either, right? What I didn't give you was this, I think we did this one in class, that's why. 7 we did in class together, right? Yeah. Okay, that was the tougher one. And we did that, I know, that's why I changed this whole thing. This one we did in class. So 6, you were okay with that? Pretty much the same thing? Okay. Point of discontinuity again. There were no zeros of your numerator because once you factored this out, guys, don't forget you get a 1 up here. This is your reduced function. So now there's no zeros of your numerator, and you can tell you have no x-intercept and you have no y-intercept because that's your asymptote. When your numerator is less than the denominator, it is y equals 0. So your x-axis and your y-axis are both natural asymptotes here.
What's the horizontal asymptote?
The y equals 0. Somewhere it got cut off also. It was right over here. So y equals 0 is your horizontal. You have no slant. You have the point of discontinuity, the one that you factored out. It's fair just in case one is taken away. That's pretty sad when security says, yes, she'll be back. All right, any questions on this? Where did I put my point of discontinuity? Right over here. So your point of discontinuity is the factor that you factored out of here. Remember to bring that factor down somewhere, set it equal, and then plug the 3 into this reduced one. So y is equal to 1 over 3. So your point, and you have to get an xy point for this. Again, if you put this in your calculator, your table will say 3 error, but you can do a 2 point. So as the limit, as x approaches 3, we can do if x is 2.99999 and if x is 3.00001, it will say y is 0.33333. It'll look like 1/3. It'll approach that point from both ends. You're getting a little preview for next year in here. Of course, there's a lot of different ways that they work their limits, but for us, we do this. And don't forget to remove that point from your domain. Do that first, and remove that point from your range. And from any of your concavities or decreasing, increasing, make sure you remove that 3. Because it doesn't look like it in your graph. So make sure you somehow make an open circle so that we can see that there is no point there. Good? Make sense? And Marie, what's the trouble? You don't like that part, right? Let's put this in. We have time. Let's put this in. This is an easy one to put in. Hopefully my calculator will cooperate. Alright, so let's graph this. So you can kind of see your asymptotes at work here. You can see your asymptotes. And right now, this looks like it's going right over the 3, because it can't go any differently. So if I go to my table, I shouldn't be able to use an x of 0, and I shouldn't be able to use an x of 3. And sure enough, I can. The x of 0 is where my asymptote is, because that was left in my denominator. So when I come down here, that becomes my vertical asymptote, x equals 0, which is my y-axis. Okay. My point right here, where the 3 is right over here somewhere. And I have to figure out what that is. So if I do this, and I say let's put in a 3. 3 says you have no point here. There's no point. So if I say, okay, let's approach it from the left side. Oops. Let's go like this. Isn't that 1/3? 0.33333? Now let's approach it from the other side. Let's do this. 3.000001. I can certainly find a point for this. And look where it would be. So see this little blinker thing? If I approach it from the left and I approach it from the right, it's going to be this y value, which is 1/3. And we can find that algebraically, but after we reduce this, we plug the x in to find the y. Don't plug it into your original one because it will be undefined. Because it's really a point that doesn't exist. But as we approach that point, we can find the point that it would have been, which we call a limit. Does everybody see how to look at that through your calculator? Be careful on your point of discontinuities, because when you look at your graph, you certainly don't see it.